Actually, Thomas has already given the talk. Thank you. I mean, really, thank you for this very nice introduction. So, as Thomas said, first of all, let me thank all the organizers and the program chairs to invite me. Thank you very much. This is actually not the first time this is actually probably the first time I give an invited talk something like a few hundred meters away from my home. And but it's not the first time I give an invited talk at KR. 14 years ago, I was an invited speaker for KR in Trento. So we are getting close to my home. And probably I hope to be invited for KR 2040, giving a talk from my living room. And maybe 2014 in my bedroom. Anyway, so the topic is ontology-based data management. I would like to introduce the topic, the motivation for this kind of work we are doing. Actually, the only correction I want to make to Thomas' introduction is that I did all these kind of things with my colleagues, with Giuseppe, Riccardo, Domenico, Diego, Marco, Francesco, and so I'm talking about we rather than I. And so what is the motivation of the work that I'm going to present? Well, those of you who teach databases know very well that we start our course essentially by saying that before the database management systems area, situation was like this. We had many different data sources and and essentially these data sources were for application, for procedures. So we had a situation where the data were spread over the data sources, and they were essentially used by application. With the notion of database management system, the idea of a single database, of a single repository for all the information of an organization came out, and so a database management system really is a tool for realizing this idea of integrating all the data of a single organization into one repository and having all the applications looking at this data. The problem is that the situation right now is essentially the same situation we had in the pre-DBMS era. If you look at many database information systems in organizations, real organizations, probably big organization, but also medium-sized organization, situation is exactly the same that we had before the database management systems. We have distributed, redundant, application-dependent, and mutually incoherent data in the various data sources. And still, these various data sources serve more the application rather than representing a coherent and conceptual unified view of the data. On the other hand, this conceptual and coherent and unified view is desperately needed for several reasons. For example, for the management of the organization to have, to make decisions based on information in the organization, you really need a conceptual unified view of the data. So, just to give you some example from a fragment of a real-world example, this, what I said, is true also for just one data source. It's not necessary to think of a set of data sources, just one data source. This is one fragment of a relational table used in a bank information system. It's just a huge table with several columns. And for example, this is a table for customers. Essentially, each tuple represents a customer in the bank. And there are several rules that are hidden in the tables. For example, a negative value in the first column denotes that the customer is actually a holding, is a particular customer. Then you find a lot of flags, like flag CP. If you find for a particular tuple an S there, this means that the corresponding customer is a leader of the group it belongs to. There is a notion of leader, but there is also the notion of head of the group, which is a slightly different one. And this is taken care of another column. And for example, this other flag means the value n means the field that another field fatturato is not valid. I mean, this is really something that is for applications. It's not for querying really the data. It's just for applications. So and this problem obviously makes a lot of other implications. And so that enterprises spend a lot of time, and a great deal of time and money on information integration. A recent publication by Gartner says that the market for information integration software is estimated to grow from $187 billion in 11 to 2,079 billion in 2015. And so still data integration is a very, very important problem from the practical point of view. And although, I mean, it's, as Thomas said, it's a very long time that several people advocate the idea of integrating data from a conceptual point of view. So, what is the talk that I'm going to deliver is about an idea we had, say, something like 7 years ago, to somehow tackle this problem from a knowledge representation and reasoning perspective, and with the following principles. First of all, leave the data where they are. And this is a principle that is very important from a practical point of view. You cannot simply, restructure the information system. You cannot just, stop the word and build a new system. You have to leave the data where they are and try to do something with the data that you have. Build a conceptual specification of the domain of interest rather than the data in terms of knowledge structures. Then map such knowledge structures to concrete data sources. Express then all services over this abstract representation, and try to set up a system that automatically translates services from the conceptual level to the data services. And that was our program. And the nice thing was that at the time there were several companies that were eager to collaborate with us, and we had already several contacts with companies, and then in the following years we had the possibility to experiment this idea in several applications that I'm going to talk about a little bit later. So what is the idea then of ontology-based data management? Can be summarized as follows. You have your data sources, you leave the data sources as they are, you build an ontology, which is a conceptual representation of the domain of interest, and you build a mapping. So that then a user can interact with the data by means of the ontology, by means of, for example, querying the ontology. And the idea is that instead of just looking at the table that we saw before, you can talk about customers, groups, and you can talk about the concept and asking information, and hopefully the system is able to translate these queries over in terms of the data source alphabet and mechanisms. Obviously, you need these mappings, right, to relate the data to the ontology, and this will be one of the real problem in this kind of system. So what I'm going to do in the following half an hour, I will try to be brief. But anyway, I will first of all talk about a little bit about the formal framework, which is very easy. It will be based on logic and description logic. Then I'm going to talk about several problems, like answering queries, how to answer queries in this setting, how to deal with the problem of inconsistency, because when you have these data sources which are independent from the ontology, obviously it might be that your data is not coherent with the ontology, with the conceptual view. So you have to deal with this problem. And also, when I said that the customer in this, the client in this particular system want to express services, I'm going to talk about not only queries but also updates. Once you have defined the ontology as a conceptual model of the domain, then the client might want to express the update instead of in terms of the data sources instead of the ontology. So you have also the problem of understanding how to carry out updates at the ontology level. Then I'm going to talk about challenges, because I believe that the research in this field with this particular characteristic that I'm talking about is really at the beginning, and there is a lot of potential. So the framework. The logical framework is very simple. For me, an ontology-based data management system is just a triple, O, S, and M. O is the ontology. In this talk, I will talk about description logics ontology, but in principle, you might think of any first-order logic or any logical theory that expresses your domain in terms of a declarative specification. Then S is a relational database. For me, actually, in this talk, I'm going to assume that your different data sources has been federated into one single database, okay, which essentially is an SQL database that we can map the ontology to. And the mapping is expressed in terms of special assertions, and the kind of assertions that you need to express the relationship between the data at the sources and the ontology is essentially a sort of a view-to-view mechanism. There are many mapping languages out there. Some of them are very restricted. Some of them are just mechanisms to map one element of the alphabet at the sources with one element of the ontology. We believe that in practical settings, you really need a very expressive mapping language that allows you to express relationship between any view of on the data with any view on the ontology. So in principle, you might need this kind of mapping language. Having decided that the ontology is a logical theory, then the semantics is very simple. Actually, semantics of the whole thing is what is obviously a set of models, a set of interpretations for the ontology. Okay, the ontology is the object that really counts for the client. So a model for the whole thing is a model for the ontology, and also a model that satisfies the mapping with respect to the data sources. And obviously, I have to tell you what does it mean to satisfy the mapping, but in principle, the idea is very simple. You have your database S, it's a state of a database, it's just a database that you can consider a first-order structure, and then to satisfy the mapping means that this logical implication is satisfied by the model I, the interpretation I. So I'm going in this talk. Indeed, I'm going to model the mappings like logical implication, and in fact, here I'm talking about sound mappings in the sense that the mapping goes from the sources to the ontology. And now the point, if we accept that this kind of system is formalized in a very simple way like this, then we have immediately at least three questions, very fundamental questions. Which language are we going to choose for the various elements of the various components of the system? And in this talk, I'm going to talk about the possibility of using description logics to model the ontology, and I will talk about kind of different languages that can be used for the various other components. But the main point, obviously, it will be the compromise between the expressive power of these languages and the possibility of really, reasoning about the whole thing and realizing the idea of translating the services from the ontology to the data sources. So, by the way, in this talk, I do not have the time to talk really about the mapping. So what I'm going to do right now is to assume that the mapping is a particular kind of mapping that is called GAL, and I'm going to work with what I call MS. MS is what? It's the application of the mapping to the sources in order to transfer the data from the sources to the alphabet of the ontology. And now, for this talk, I can assume that this MS is just a set of facts built on the alphabet of the ontology. Okay, so this is a way to abstract from the mapping in this talk, because I don't have the time to really talk about the mappings. At the end of the talk, I will mention some of the problems with the mapping. But for the moment, let's abstract away the mapping, and so that this MS is actually a set of facts that comes from the data, but is expressed in terms of the ontology. So in terms of description logic terminology, this would be an A box. Okay. But this is just for this talk. I mean, in practice, obviously, the mappings are very important. So now the problem is, having with these formal objects, what can we do with it? Well, first of all, we can try to realize the idea of ontology-based data access and integration, which means what? At least to try to express the queries over the ontologies, and then having the system computing the answer. And in this talk, I will briefly talk about this problem, together with the idea that in general, inconsistencies may arise. Inconsistency means that using the classical first-order logic mechanism, the semantics of the system is empty, actually. The semantics of the system is empty, so we should do something about it. And I call this problem of trying to answer queries even in this setting, inconsistency-tolerant query answer. If I will have the time, and if the game with Germany and Holland has not started yet, I will talk about the database update problem in this setting. Okay, but only if I have time, don't worry. By the way, there will be a general requirement that I have to follow in all these kind of topics that arises in ontology-based data integration. By the way, the other items, I will discuss them at the end as a future work. But there will be a theme, a general theme that is very, very important. You have to understand that we have a lot of data in the sources, a huge amount of data. Today, organization means that we have, a very huge amount of data that are in the sources. So what is very important is to ensure that the complexity of the whole thing is reasonable, at least with respect to the size of the data, at least. Okay? And in fact, I'm going to talk about data complexity, which is the complexity of the various services with respect to the size of this MS, the set of facts coming from the data. So, my first, what I'm going to tell you right now is a sort of story about what we did to answer queries in this kind of setting. Obviously, in principle, you are interested in a very powerful query language, right? If you go to a database person and you ask, which is your language, essentially he says first-order logic, in the sense that he says SQL, which is somehow at least first-order logic over a database. So in principle, you might use first-order logic as a query language to your database. But we will see that this is just a dream, and so we have to consider also subset of this kind of query language. In fact, I'm going to use a lot conjunctive queries, which is a restricted form, obviously, of first-order queries, and I'm going to write them in data log notation, which is essentially just a conjunction of atoms that corresponds to select, project, join in relational algebra. So it's actually a very important class of queries. And also I'm going to talk about union of conjunctive queries. So what does it mean to use this kind of formulas for query? Just a very simple example. You have this very simple ontology expressed in terms of a sort of ER modeling. This ontology says that Heights is a relationship on persons. A computer professor supervises some person. Computer professors are partitioned in computer scientists and computer engineering, and you might, for example, express the query, tell me, give me all X such that supervised by XY, Y is a computer scientist, Y hates Z, and Z is a computer engineer. That's a very simple query. The idea is that if you use first-order logic, where the atoms are the alphabet, belongs to the alphabet of the ontology. That's it. Very simple. And obviously you have, we have the notion of models of the whole thing. So we also have implicitly the notion of answers to a query. What is an answer to a query? We consider what we call the certain answers. The answers that are true in every model of the theory. Okay? So when you have a query expressed over the whole thing, you want to compute those answers in terms of the constants of the alphabet, those answers that are true, that are those tuples that are the answer to the query Q in every model of the triple. Obviously, our dream was to at least use first order logic, but as soon as you try to use first order logic, you realize that actually this is an undecidable task. Why? Simply because we are not in a database setting where we evaluate the query over a single structure. We have to compute the answer in every model of the theory, so you can actually express validity as a query language, as a query answering task. So first order logic is undecidable. That's why we immediately restrict our attention in this talk to unions of conjunctive queries. Okay. So from now on, queries means union of conjunctive query. So let's see what happens. Let's try to see an example and to understand why it's not immediate or it's not simple to answer queries in a setting like this. We have our ontology, and we have now the facts that comes from the data by means of the mapping, and the facts are the following. John is supervised by Andrea, who is a computer professor, is supervised also by Mary, who is a computer engineer professor. No, sorry, it's a computer professor. And I know that Mary hates Andrea, and Andrea hates Paul. Okay? Now, this comes from the data. Now the query is, give me OX such that X is supervised by Y is a computer scientist, Y hates Z, and Z is a computer engineer. So what is the answer to this question? Well, one could try to see if I find this Y here, right? And see if, for example, X can be John. So I know that John is supervised by these two people. I can try to match the query, the variables in the query. What is your guess? What is the answer to the query? Is there anyone who satisfies the query? Oh, by the way, I have to tell you, sorry, that the ontology, as I said before, computer professors are partitioned into computer scientists and computer engineer. Okay, it's a partition. So the point is that although it might seem that no one satisfies the query, right? Because if I try to substitute the various objects to the variables, I do not find any substitution that is right. The problem is that the answer is John. And why is it? Because I know that Mary is a computer professor. It's a computer engineer. I don't know why it doesn't. But anyway, it's a computer engineer. It's a computer scientist. Here I know that Andrea is a computer professor, and so either in every model, either Andrea is a computer engineer or is a computer scientist. Now, if John is a computer scientist, then if Andrea is a computer scientist, then the path John, Andrea, and Paul is the one that I look for. If Andrea is a computer engineer, then the path like John, Mary, Andrea is the path that I'm looking for. So this means that I have even for very simple conjunctive queries, very simple ontology languages, I have to reason by cases to answer the query. Okay, very simple ontology language, very simple conjunctive queries, and in fact, what we can show immediately is that although in the case of a plain database, the data complexity is in log space, okay, For example, in Now Tool, which is a language, fairly expressive language for ontology representation, then query answering, data complexity of query answering is co-NP high. And actually, this is true already for a very, very simple T-box with the single disjunction. So, after this observation, the question is, you might remember we have a requirement here in this ontology-based data management setting. We have a lot of data. So we cannot just accept a co-NP hardness problem for answering queries. So the question that we started studying was, can we find interesting description logics for which the query answering problem can be solved efficiently with respect to data complexity? Okay. For example, in log space, remaining in log space with respect to data complexity as it was in a traditional database setting. Obviously, if yes, if we can find some interesting description logics of this type, can we leverage relational database technology and relying on this technology for answering queries? Now the idea that we had was the following, essentially. The idea was trying to see if a rewriting approach worked. What is a rewriting approach? In principle, when you have an ontology and a query, and then the A box A, let's say, now I'm talking about the A box A, but as I said, this might be simply the materialization of a set of facts coming from the data. In principle, you can always think of query answering as divided into two steps. Okay, one step, you consider the query and the ontology, the axioms of the ontology, and you compute a new query. Let's call it RQO. This query now can be used to evaluate over the structure corresponding to the database. Now it's an evaluation. The second step is just to evaluate the query. In principle, you can always do that. The real problem is, which language do you need for expressing the rewriting? Okay? So the question is, which is the language that I need to express these objects? Okay? So in principle, if you do not pose any restriction of the language, you can always do that. But if you have some restriction, for example, you might say, I want to rewrite into SQL because this is what I have over the data sources, then the problem really changes. And so you have to understand that you have to limit the expressive power of these two guys here in order to understand whether this approach works for a particular ontology language. So if we introduce the notion of Q rewritability, what is Q rewritability? Let Q be a class of queries or a query language, let's say, and L an ontology language. Then for an ontology language L, query answering, I say that is Q rewritable if for every T box O of the language L and for every query Q, the perfect rewriting of Q with respect to O can be expressed in the query language O. The query language Q. So it's Q rewritable if the rewriting can be expressed, the rewriting that really, when is evaluated over the database, returns a certain answer, can be expressed in the query language Q. So obviously the expressiveness of the ontology language affects the query language into which we are able to rewrite conjunctive queries. When we can rewrite into union of conjunctive queries, so if the language of the ontology is such that I can produce the perfect rewriting in the language of union of conjunctive queries, then I can really rely on database management systems. You should remember that database management systems are very good at executing union of conjunctive queries. Okay, very, very good. They are essentially the optimization that they are able to do is for the class of union of conjunctive queries, essentially. So when you can rewrite into this class, you can really use relational database management system as a way to evaluate the query over the sources. If you cannot rewrite into union of conjunctive queries, but let's say in first order logic, Still, you can use a relational database management system because evaluation can be done in SQL, although it is not true that every SQL query are efficiently performed and executed by the database management system. When you can rewrite into non-recursive data log, when you need the power of non-recursive data log to rewrite the query and to produce the perfect rewriting, then you need, can you still rely on database management systems? It's not clear, in the sense that at least you have to use views, okay? And it is not clear whether the relational database management systems are very efficient in using the views. Actually, there are experiments that show that they are not very good at using, without any mechanism, particular mechanism, the views. And then when you can rewrite into an n-log space hard language, then you need at least linear recursion. And when for expressing the rewriting, you need a p-time hard language, then you need data log, okay? And obviously, finally, when you can rewrite into a common p-hard language, query evaluation requires at least disjunctive data. Now, the point is that when you are in front of this picture, you have to understand that in practice, what the organization really use, they are relational database management systems. They are not using data log, okay? Although data log is promising from several points of view, although there are several research prototypes which are interesting, in the real world, no one uses data log, okay? And it's very important, and that's why we wanted to try to see what happens if you want to rewrite into union or conjunctive query assertion. And actually, the idea is that the kind of language you have really determines the kind of rewriting that you get. Let's see another very simple example. Let us reconsider the ontology that we saw before, and let's add a new axiom. Say that the computer scientist hates only computer scientists. Okay? Now, I have this very simple query, computer scientists. What is the perfect rewriting? Can I rewrite this query? Very, very simple query. Now what has changed is simply this axiom. Can I rewrite this query into SQL? Well, it's very easy to see that you need actually the transitive closure here. Because the query, the perfect rewrite is the union of computer scientists and with union computer scientists y 8 plus, which means that the recursive closure, the transitive closure of 8 with respect to yx. And this is because of the axiom of the ontology. You know, in order to get a certain answer, you need the transitive closure, which is not expressible in first order logic. Okay. Now the point is the question now that we were interested in answering was: can we find interesting description logics for which query answering is first order rewritable, or even more specifically rewritable in union or conjunctive query? That's the point. And what we did is to find an answer to this question. We introduced the family of description logics of DL-Lite. Now I'm going to talk about a particular member of this family, description logic called DL-Lite AID. But there is a family of the DL-Lite description logic that you can use that have, all of them have this property of being first order rewritable in union or conjunctive queries. What is the DL-Lite? It's a very simple language. I don't have the time, obviously, to illustrate the whole language, but what I can tell you is that essentially what you are doing here is to model by means of a set of axioms sort of UML diagrams, okay, ER diagrams. I mean, the kind of formalism that the people use to express the conceptual schema, the conceptual model of an organization. Okay, so you have this kind of mechanism. You have inclusion assertion between classes, disjointness between classes, domain and range of properties. For example, you might say that a certain range of a property is a certain class, and the domain of a property is another class. You can accept mandatory participation. You say that every instance of a class participates in a certain role or in a certain inverse of role. You have functionality of relations. You can impose that a certain relation is a function. You have also inclusion between roles, relations, between binary relations, and disjointness between binary relations. Okay, this is the L-Lite AID. Actually, we could extend the language a little bit, as shown by Artal et al. In 2009, but essentially this is the language of the L-Lite. And so, now, in 2 minutes, I wanted to tell you what happens if you try to look at the problem of answering queries in this language. Okay? So, first of all, I mean, the idea of answering queries with an incomplete information context, which is the context of ontology-based data management, is not new. You might try to use, for example, techniques developed in database theory, which is, for example, the chase. The chase is an old technique in database theory. Essentially, it is a procedure that, starting from a database, it completes the data according to a set of integrity constraints. And you can consider the ontology as the set of integrity constraints that you want to consider. You can consider our A box as the database, and you could try to apply the idea of the chase to our setting. The problem is the following: that the characteristics of the L-Lite are such that if you apply the chase may not terminate. Okay, so the L-Lite does not fall into a class of integrity constraints for which the chase is guaranteed to terminate. So, to put it simply, we could not use the theory of the chase and a lot of database theory results to understand and to come up with an algorithm for query answering in the L-Lite. Also, if you apply the solution as such to the L-Lite, this doesn't work, because again, the solution without any mechanism would not terminate for this kind of language. So what we did is to design a new algorithm called PerfectRef, that we then implemented in our tool, which is called Mastro. This is a special algorithm dealing with this kind of language, the L-Lite. Fortunately, I don't have the time to go through the algorithm, but the main point of the algorithm is that let's try to do it by example. It is the following. The main point of the algorithm is the following. You have your conjunctive queries. Let's say, for example, this query, Professor X. And you have axioms in your ontology. For example, you have the axiom that the associate professor is a professor. You use these axioms as a rule, as a logic rule, and you rewrite your query by substituting professor with an associate professor. Okay? So this is a basic rewriting step. You have to be careful not to, to understand which are the conditions to terminate. But this is the basic rewriting step that you can do. A second rewriting step, which is very, very important, is the reduce step. The reduce step takes a query. Let's say that your theory is teaches xy and teaches zy. Okay, you have this rule. Professor, which implies there exist teachers. Now, this does not apply to our conjunctive query, because y is a join variable, and so I cannot rewrite neither teaches, the first atom teaches, nor the second one. On the other hand, if we now unify these two atoms, and we get from the two atoms we get the new query teaches xy, then I can apply the rule and rewrite the original query into professor. So So this very simple example shows that you need another rewriting step besides the inclusion, the basic rewriting step that I showed before. This is the reduce step where you try to unify the atoms of the query, and in doing that, you can then use more rewriting steps in the following. So with these two basic steps, we were able to show that you have an algorithm for query rewriting, which means what? Essentially, you start with the query Q, which is a union of conjunctive queries, applies to Q all possible ways the inclusion in the T box. The nice characteristics of description logic DLite is that the size of your query does not increase. It's always the same. And then you also unify atoms in such a way that the new rules can be applicable. And this is essentially the algorithm, and we prove that the query resulting from the above process is a union of conjunctive query and is the perfect rewriting of the original query. So you can now take this query and you evaluate the query to the data sources. Okay. Now, this was very important for us. What we did is to immediately experiment this algorithm in the real world settings that we were using with collaborations with several companies. Now we experimented, and unfortunately we had a sort of surprise in the sense that although the query, the union of conjunctive query, exactly was an SQL query, the point is that depending on the kind of ontology that you had, the size of the query that the algorithm produced was very, the size in terms of the number of conjunctive queries. So, as I said, the rewriting algorithm rewrites into union of conjunctive queries. Every conjunctive queries in the union has the same size of the original query, but the number of queries in the union might be enormous, depending on the ontology. So, and in fact, actually, the complexity of the algorithm is such that the size of the query is in the exponent of the complexity function, and therefore, I mean, it was obvious that in the worst case it could be exponential, but we didn't really think that in practice this was a problem. So. But this was a problem. Actually, this is just 1/5 of an ontology that we produced in the first experimentation. And you see there are a lot of ISA relationship there. It's not very visible, but you can imagine there are a lot of ISA relationships, which makes the problem of computing the rewriting hard. And actually, in the first experiments, we realized that the perfect ref algorithm works for queries with at most 7, 8 atoms, let's say. Okay, so, but queries in the real world are much more large. Okay, for example, in this experiment, queries might be something like 12, 15 atoms, and we had really a problem in dealing with this problem, with this manifestation. So the problem is this a bug of our algorithm? Can we rewrite the original query in a much more clever way, in such a way that the query that is sent to the data sources is not such a large query? Well, you can, for example, experiment and try to understand if there is another method. Okay, one might say, the idea of the rewriting is wrong. Okay, why don't you just take the database and produce another database in such a way that your query could be evaluated in this database? Now, this idea does not really work in general, because we have proved that for our language, the DLite AID, given MS, given your set of facts, there is no finite database B such that for every query Q, the certain answer coincides with evaluating the query over this database. So you cannot just build a new structure, forgetting about the ontology, and then evaluating the query. What you might do it query by query. Given a query, you might try to build a database that is the right size for the query, but you cannot do this in general. So, what can we do? We cannot just materialize in another database, and one could try to apply the chase only partially. Instead of just materialize the whole thing, you could try to materialize a certain kind of set of facts, and hoping that then the rewriting step, since you know that you have this object already pre-computed, is small. And there is a nice attempt and a nice approach by Konchakov et al. Published in KR 2010 that tries to do this, what they say, they call it a combined approach. They just materialize part of the objects and then rewrite the query. Unfortunately, this works only for role inclusions. For a language without role inclusions. Okay. But unfortunately, in our experimentation, role inclusions were very important for modeling the domain. And also, it's not clear whether in practice this idea of materializing the data is appropriate for ontology-based data access. Because in general, organizations, they don't like to materialize the data again. They have it in the data sources, and they don't want to move the data again with the additional problem of keeping the two copies up to date. So there were a lot of other attempts to trying to solve this problem, or at least to address this problem. For example, there is now, in 2009, there is a paper illustrating a new system called Requiem, a new algorithm for answering queries in DLI, actually answering queries in a more expressive description logics, that in the case of DLite, it rewrites the query into a union of conjunctive queries again. Okay? So that's another algorithm which is much better than perfect ref, actually, because it reduces the number of reduced steps. Actually, the reduced steps is responsible, one of the responsible for this blow up of the query, and the algorithm nicely finds conditions by which we can reduce the number of reduced steps in perfect ref, but unfortunately the size of the rewritten query is exponential again in the worst case, even in this new algorithm. I mean, there has been a lot of other approaches. For example, Rosati with Presto. Presto is actually the algorithm that we now use in Mastro, and Presto is an improvement of perfect ref. Why? Because, put it briefly, it is the size of the rewritten query is now exponential with respect to the number of particular variables that you have in the query. It's not with respect to the size of the number of atoms of the query, but with respect to the size, to the number of so-called eliminable existential join variables in the query. And in principle, in general, at least in many experimentations that we have carried out, the majority of existential join variables in a conjunctive query are not eliminable. So there was, with Presto, a dramatic reduction of the size of the query. We can now rewrite the queries of the first experimentation very easily. Presto is able to do a very good job with queries with about 30 atoms. There is also a lot of work trying to address this, but still Presto rewrites into, in the worst case, into a union of conjunctive queries whose size is exponential again. Okay, so there is now the question of whether is it really avoidable. In last year, Kikot et al. Published a very nice result that shows that it is actually not avoidable. The theorem that shows that is the following. Checking whether a certain tuple is in the certain answer of a query is NP-complete in combined complexity, even if the ontology is in a very, very simple DLite description logic, and the set of facts is constituted by just one atomic assertion. Okay? What does it mean? Well, it means that since answering a first-order logic query over a database that of the form A, C can be done in linear time, it follows that no algorithm can construct a first-order logic rewriting in polynomial time unless P equal NP. So we cannot rewrite in polynomial time, and therefore decide in polynomial time when you have DL light and we have a conjunctive query. There is a lot of work going on. Even in this conference, we have a lot of papers dealing with this problem. For example, we have this a paper here by Gottlob Schwentig showing that polynomial rewritings exist if we allow rewriting to be expressed in non-recursive datalog queries. But again, if this is practical or not is questionable. You might remember that datalog, non-recursive datalog in practice is not easy to evaluate. And also the reduction they have use additional symbols. And so there are anyway a lot of investigation, and I suggest you, if you are interested in looking at a number of papers dealing with this problem. So, don't worry, I have a modular organization. I can skip I can rewrite the presentation, okay, into a presentation
exponentially many parts.
Into a presentation that allows you to watch the game. No, I can just keep the problem of inconsistency tolerance, but I think you can believe me that the problem of inconsistency is a very important one. Suppose you go to a company, you build the ontology, you build the mapping, and then you say, okay, I cannot use Mastro. Why? Because the data is inconsistent with the ontology. Okay, good, very good. They will disappear and they will never come to you. So the point is that we should do something about the situations where the fact of the database is incoherent with the ontology. Okay? So what we did is to try to apply an idea from database theory, in particular the notion of repair, to deal with this problem. And if you are interested, I can obviously point to the papers and to the various papers we are writing on this subject. The main point is that with a particular semantics for inconsistency tolerant query answering, you can still rewrite in first-order logic when you have a real-light ontology and conjunctive queries as language of queries. You can still rewrite. You accept actually, a sort of weak kind of semantics for inconsistency tolerance, but at least you have a means for trying to answer queries, even in the case where your data are not coherent with the database. I want to skip all of this, and I want to go. So, 2 words about the update. As I told you, we had forced experimentation with different companies, and it is very, very surprising. Then, as soon as they understand the approach, they ask you for updates, and they ask you, why should I just put queries on the ontology? Why am I not allowed to express updates on the ontology? So they would like to use this object. There is a reason why, because building the ontology is a very expensive task. So if you accept to do it, you have done an investment, and you would like to use these objects not only for just querying, but also for expressing all the possible services. If the system works, and if the system is able to do it, that would be great. So you have also the idea, the question of expressing updates over the ontology with the additional problem of first understanding which is the semantics of the update. It's not completely clear. It's not just updating a database, it's updating a theory. So you have all the problem of belief revision and updates. And with the additional problem of pushing the updates to the data sources. I mean, once you have decided what to do with the update at the logical level, you still have to decide what to do with the data sources in order to reflect the update that you have decided to apply. Anyway, let me conclude the talk by telling you that this is a very, very rich field. There are a lot of problems, okay? This very basic idea of having the ontology and trying to build a system that that accepts services expressed over the ontology and translated to the source is a very rich idea that creates a lot of problems. For example, as I told you, I mean, efficient query answering is still a very active area of research. Pushing the updates to the data source is a very important problem, but also updating inconsistent ontology-based data access systems. If you accept to have an inconsistency and you are able to query an inconsistent system, why do you want to update an inconsistent system? So what does it mean to update an inconsistent system is also a very interesting idea to pursue. But also, I mean, once you have this ontology on top of your system and people are using it, why don't we try to use it for sophisticated tasks? Not only answering queries, but business intelligence, for example. Business intelligence can be seen as a task where you need sophisticated form of queries. So we really need to go beyond conjunctive queries. So, which is the idea to go beyond conjunctive queries? We know that first-order logic is undecidable, so we have to do something. We have to find a way, probably to weaken the semantics of first-order logic, to extract usable information from rich queries with a good semantics, trying something to deal with this problem. Then you can use the ontology to do data quality. Data quality means that you can use the ontology as a model of your universe of discourse and therefore to measure the quality of the data with respect to the ontology. After all, what does it mean that my data has low quality? It might be two things. One is that the data are not aligned with the reality and that it's very hard to deal with. I don't know what to do. But the other thing would be that the data is not coherent with the ontology. And so at least trying to measure how much the data is aligned with the ontology, it can really be done. And I can show you that usual query answering does not really meet this objection. You have to play with the whole system to really express interest in data quality services. Also, and finally, once you have accepted the idea of modeling your domain in terms of the ontology, why can't we try to model the processes also of the organization? That's another thing that people asked us. Okay, you have connected our ontology with the data. What about the processes? Processes are very important in an organization which has an information system. So modeling a process in terms of the ontology is also very, very important. So there is a very rich problem here, which is a good language to model the process, which are good algorithmic problems to try to analyze the process of the ontology. For example, to understand the properties of a process or to help the process re-engineering. There is a lot of work that can be in principle done on these kind of things. Also, another thing that people always ask is, can I now query the ontology in natural language? For some reason, they think that the ontology, calls for natural language. So they ask for querying the system in natural language. And finally, there is the need of effective tools for modeling both the ontology and the mapping. I don't have the time to show you real ontology that we have developed, real mappings. We are talking about 500 mappings, which means assertions from the data sources to the ontology. We are talking about 300 concepts something like 300 axioms. And very soon, it's very difficult to deal with this specification. You have to have tools for helping the development. And we do not have strong tools to help the designer. For example, you have your system, you change the ontology, which mappings should I change? I mean, it's a very big problem. It's actually it is the biggest problem that we have right now in our experimentation. And it's nice that University of Rome, together with the other partners, some of them are here, we will start a new European project called Optique, working on the specific problems of ontology-based data access, and we hope that some of these questions will be addressed in this project. Okay, so finally, this is the end of my technical part, but I want to thank a lot of people that have worked with me in this last 7 years. Obviously, the original group of people that started with this research was myself, Calvanese, Diego Calvanese, Giuseppe De Giacomo, Domenico Lembo, Riccardo Rosati. Unfortunately, after a few months, Diego Calvanese decided to leave the country, so anyway, there are also additional people in this current group. I want to mention Antonella Poggi, Marco Ruzzi, Domenico Fabio Savo, Cristina Civili, Valerio Santarelli, Riccardo Mancini. Unfortunately, what I really miss is Marco. Marco actually started working on this subject, but then he unfortunately passed away. So since we are in Rome, I want to dedicate this talk to him. Thank you very much.
Questions, please. So there are these two communities. The integration community is completely averse to materializing data, and the exchange community is completely averse to rewriting. And I'm really puzzled by this ideological rigidity. And in the face of exponential blow-up, maybe you should be a bit more flexible and allow some materialization. And equally well on the other side. Somehow I don't understand how we split ourselves into two camps, that each one has its own commandment. Thou shalt not rewrite, thou shalt not materialize.
I completely agree. The point is that in none of these collaborations they wanted to materialize data. I convinced them.
I mean, yes.
Well, the point is that they have already, but there is a psychological problem also. They have already spent a lot of money on data warehouses. In the last 20 years, companies like, I don't know who is here, IBM, convinced them to build data warehouses. Now, data warehouses has not been a solution to all this problem. Okay? So and also, people in data warehouse, they talk about on-demand data integration, on-demand data warehouse, real-time data warehouse. They don't want to materialize. I'm not saying that, I mean, obviously, if you're interested in materializing, there is a lot of work to do. But what I'm saying is that we had constraints. The constraints was, I want to use a database management system like this.
You mentioned that, okay, of course there are many open problems. Probably one of the ones that have worked most on the community is just variance in search, which is still not feasible for large queries. But we all have the problems, I mean, something we have discussed a bit now in the workshop, that, I mean, there are a lot of alternative writing techniques and so on, and everybody keeps testing their writing technique on very simple benchmarks with tiny queries which are handwritten. And I mean, I think only Mastro has been tested, or is I mean, with real queries and real ontologies. I know that you have these industrial partners and there are serious privacy issues that they don't let us do. But do you see any possibility? I mean, how can we get a good benchmark that allows us to really know whether the other techniques that use other things that is slightly more, I mean, that writing some kind of recursive data that would allow us to really test on something that's somehow might be similar.
I agree completely. We need the community really needs that. What I can say that we didn't do it because in the last 3 years, the last 3 or 4 years, we had no time. I mean, dealing with industries. You know, I mean, Italy doesn't have money anymore, right? No money at all. So we
borrow from Greece.
So 4 years ago we decided either we find industrial partners that pay or we are dead. So I cannot do it, but I completely agree with you that it would be nice to have. I personally, my group cannot do it right now, but the idea is great.
So any further questions? Comments? Well, if not, then let's thank the... Okay. Sorry.
One question that comes to mind is originally when ontologies were proposed, I mean, the emphasis was on semantic web. And this is a very different sort of use of that. And I was wondering if you had any comments on this.
To be honest, I don't believe in the fact that these kind of things might apply to the scale of semantic webs. The things that I'm studying right now and the collaboration we had are very specific. They have ontologies like, some hundreds of concepts, mappings, and the mappings, I didn't talk about the mappings, but it's a very big deal. I mean, building a mapping is, it's a lot of effort with the data sources. Now, I don't know, I don't know, I don't think this can apply easily to the scale of the semantic web. But the answer is really, I don't know. I'm not saying no. I don't have the elements to really say something more significant.
Any further question? Well, if not, then let's thank the speaker again.